This video is going to cover Newton's second law of motion. So it's just going to finish out that packet, pages 3 and 4 in the packet. The difference between Newton's second law as compared with Newton's first and third laws is Newton's second law really focuses on the acceleration. And so that's going to be the main thing that we're talking about in this section is acceleration. So Newton's second law is not as catchy as the other two laws, first and third. The acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force in the same direction as the net force and inversely proportional to the mass of the object. That is saying a lot in there, and so this video we're going to kind of go through each part of that and what do all of those mean. First of all, we have a little symbol. This symbol, which is kind of like an infinity symbol that's been cut off, that symbol means proportional to. And we use this when we're talking about these equations quite frequently. Anything that something is proportional to another, we use this. So this is saying the acceleration is proportional to the net force. We could also say that the acceleration is inversely proportional to the mass. That's what the 1 over m means. It means inversely proportional. So acceleration and force are proportional to each other. In other words, if I double the acceleration, I will double the force. Whereas acceleration and mass are inversely proportional. So if I double the acceleration, that means I'm actually using half of the mass. Okay, when we talk about Newton's second law, we usually talk about it in terms of an equation. And so the equation is in two different forms. This is the form that is given to you on the equation sheet. Acceleration is the sum of the forces over the mass. Because remember, the forces, we can have various forces on any given mass. So the acceleration is the sum of all of those forces divided by the mass. That's how it's given to you on the AP sheet. And so it's solved for acceleration. I will tell you that frequently when I memorize it, because again, you don't have to, but if you can memorize some of these, it just makes your job a little bit easier. I always memorize it in terms of F equals ma. And so if I say F equals ma, I'm talking about Newton's second law. And so that's what I typically will kind of abbreviate it by just saying F equals ma. Okay, what this is saying, excuse me, both in the sentence up here, it's saying it, as well as in some of these different forms on the equations, is that the net force vector and the acceleration vector point in the same direction. Because if you're going to be pushing something, for instance, let's say you're going to be pushing something this way, well, whatever force that is that's pushing it, isn't that going to create acceleration in that same direction? So force and acceleration go in the same direction. Also, if an object has a net force, then it must have acceleration. That's kind of coming up here to this little piece of it. Or even to this F equals ma. If it has a force, it has acceleration. And finally, if an object has acceleration, then it must have a net force. So if something, not just velocity. Remember, we talked about the other day, if it has velocity, it might not have a force to it because something like an outer space can just be moving. But if it has acceleration, then it must have a net force. And then finally, we mentioned this the other day also, the SI unit of force is the Newton, and Newton is measured in kilogram meters per second squared, and that is approximately 0.225 of a pound, which we also mentioned the other day is about the weight of an apple. Okay, that's about how much an apple weighs, is 1 Newton. All right, let's take a look at an example. If a 50 kilogram box is pushed on a frictionless floor with a force of 10 newtons, what is the magnitude of its acceleration? All right, I'm going to take a second to draw my box. Here's my box, and I'm going to have my big fat dot for all my vectors to come out of. Of course, I have my gravity working downwards. I have my normal force working upwards. Those are canceling each other. They are balanced. If a 50 kilogram box is pushed on a frictionless floor with a force of 10 newtons, so our 10 newtons is pushing it with a force of 10 newtons, that's supposed to be a 0, 10 newtons, what is the magnitude of its acceleration? Okay, notice there's no counterforce over here. So this does have a net force. And so the question was what is its acceleration? So if we go back to that original equation that we have on the equation sheet, it is the sum of the forces over the mass. Okay, well the sum of my forces, these two forces cancel each other out. This one does not have a force canceling it out. So that's my 10 newtons divided by the mass of the object. It is a 50 kilogram box, so it's divided by 50 kilograms. Remember, another way to say newtons is kilogram meter per second squared. And so if I'm looking at my units, I can cancel out my kilograms with my kilograms, and I'm left with meters per second squared. That's what I want. And so when I work this out, 1 over 5 is 2/10, so I could say 0.2 meters per second squared. That's my acceleration. Let's turn the page. All right, let's think about if we have different masses. Let's say we have a bowling ball and a tennis ball. If the same force is applied to a bowling ball and a tennis ball, which one will have the greater acceleration and why? Okay, let's just take, for example, let's say you have a bat, like a baseball bat, and you are going to hit the bowling ball with the same amount of force that you hit the tennis ball. Which one will have a greater acceleration? Well, hopefully you can see that the tennis ball is going to have the greater acceleration. I mean, you can just imagine what's going to happen if you hit that compared to when you hit the bowling ball. So the tennis ball will have greater acceleration. Now, we can all see that in our mind. We think about it, we go, well, of course, that one's going to go farther. And the question is why? Well, why will it go farther? Well, let's think about our equation. Our equation is the acceleration is the sum of the forces divided by the mass. And the way we said this on the other page, the previous page, was acceleration is inversely proportional to the mass. So the bigger ball is going to have smaller acceleration, or the smaller ball will have greater acceleration. And so however you want to describe that, if you want to say, well, here, let's say we could say it as a sentence. We could say the force is being divided by a smaller number, resulting in a greater acceleration. Okay, I think everyone can see that the tennis ball will go faster, but you do need to understand how that comes about, what the reasoning is for it, and how it ties into the equations. Okay. Since it is possible to have forces acting in 2 dimensions, Newton's second law will have to be applied to each separately. In other words, we're going to have to find the sum of the forces in the y direction should be equal to 0, and the sum of the forces in the x direction should also equal to 0, if they are balanced. Of course, they're not always going to be balanced, and that's what's going to cause the acceleration, is when they're unbalanced forces. But when we're looking at whether or not they're balanced, we have to look at both the x direction and the y direction. When we do this, we will label the axes conventionally, and then we will determine Newton's second law that relate in each direction. So consider the example of a 6 kilogram box dropped near the surface of the earth. So here we have our box. It is 6 kilograms, and it is being dropped near the surface of the earth. Okay, well, what's going on here? We have its force of gravity. Now it's being dropped in midair. It does not have a normal force because it's being dropped in midair. So therefore it's not a balanced force. It's just 6 kilograms heading straight down. What is the acceleration of the box near the surface of the earth? Well, we know that its acceleration is going to be a negative 9.8 meters per second squared. What is the magnitude of the gravitational force on the box due to the earth, in other words, the weight. Okay, when we find weight, we call it force of gravity because it's the gravity that's acting on that mass, and that is the mass times the acceleration. And our mass here was 6 kilograms, and our acceleration is a negative 9.8 meters per second squared. So if I multiply that out, 6 times negative 9.8 meters per second squared, I'm going to get negative 58.8 newtons. And that means that I have force of gravity here is negative 58.8 newtons. I have negative 58.8. I have 58.8 newtons of force. That's the amount of force. It's headed in the downward direction. That's the negative. Okay, concerning Newton's third law, so going back to the third law, what would the magnitude of the force that the box exerts on the earth? Well, it is also going to be 58.8, but it's going to be a positive 58.8 newtons. Now, if you think about the size of the earth and how acceleration is inversely proportional to mass, so the greater the mass, the smaller this number, this is not going to move the earth very much. This is a considerable amount of force, not a whole lot, but it's not going to move the earth because the earth has a much greater mass, right? Okay, part D, how much would that acceleration toward the box be? Well, so again, we're going to use our equation of acceleration is the sum of the forces over the mass. The force we just said was 58.8 newtons. The mass is the mass of the earth. And I believe that the mass of the earth is given to you on your AP sheet. We can look that up, but I'm pretty sure it is given to you. It is 6 times 10 to the 24th kilograms. You would not have to memorize that. It's either given to you on your sheet or it would be given to you in any problem where you needed it. You do not have to memorize that. But that is the mass of the earth. And so when I work that out, it comes out to be 9.8 times 10 to the negative 24th meters per second squared. Think about how tiny that number is. Okay, times 10 to the negative 24th, that is pretty small. That is 23 zeros in front of this 9. So that's pretty small. It's not going to affect the earth very much at all just because one box is falling towards the earth. But it does affect it. Let's talk about part E. Even though the magnitudes of the action-reaction pairs are always equal, what can be said about the acceleration? So in our example, both the box and the earth had a force, 58.8 newtons. But the acceleration of the smaller object, I called it the golf ball, let's just call it the box, the 6 kilogram box. The acceleration of the 6 kilogram box was much greater than the acceleration of the earth. The earth was barely moving at all. It did not have much acceleration at all, but the acceleration of the box did have some, it was accelerating. And if we look at the numbers, the acceleration of the box was negative 9.8. We know that, meters per second squared. The acceleration of the earth is 9.8 times 10 to the negative 24th. Quite tiny. Okay, I believe that is the end of our lesson on Newton's second law. The main thing, if we had some summary lines down here, I kind of wish we did. The main thing that I would say you need to know from Newton's second law is F equals ma. And maybe more precisely, the sum of the forces is equal to mass times acceleration. Another thing that we might want to remember is that when we're talking about these forces, we are talking about the sum of the forces, and also if we have forces working at an angle, which we will eventually, we're going to start off with just horizontal and vertical, but if they are at an angle, then we have to think about the forces in the y direction compared to the forces in the x direction and how those might be working individually. Okay, that is all for our Newton's second law. We will be working on some of those worksheets regarding this in class tomorrow.